So I guess I hope you now appreciate the necessity for data and what kind of science we can do with it. I just want to briefly talk a little bit about some of the data that we're getting from this relatively new instrument, the Long Wavelength Array. This is out in New Mexico, 256 dipoles. So it's myself and many people in this room collaborating to do this work. So it's a fat dipole, or droopy dipole. Each antenna is low gain, but you combine a lot of these things and you get a very sensitive instrument. So it's a dipole in the XY plane, which you then can convert base change to the right-hand and left-hand channels, and you can get out the Stokes parameters, all the polarization components, and the output. As Baptiste showed and we've seen before, so we know that Jupiter has these cone-like emissions at various places in the northern and southern hemisphere. So those are the IO A, B, C, and D sources. And we think all the same type of mechanism there. But there's others, the lower frequency hectometric stuff and the kilometric emission that you have to be in space to observe because they're below the ionosphere cutoff. So we received some time to use this instrument to observe Jupiter. So we got a couple of hundred hours to observe Jupiter over the last few years. And just the first few observations that we've made, a few through IOB and a few through IOA and IOC. And as you can now appreciate this dynamic system where Jupiter is rotating and you've got the right IO location, this structure is very repeatable. So you get similar kinds of emissions and these really nice spectrograms using this instrument. Now, this instrument is not built for Jupiter. This instrument is built for galactic studies, radio galactic studies, and extragalactic. So just a small bit of time is being used for Jupiter. But we've seen that it's really a fantastic instrument. Look at the, sorry I don't have it on this slide, but the frequency is a very wideband instrument and beautiful polarization measurements. So we have been able to observe down to about 11 megahertz out there in New Mexico. So it's really, really good conditions and very quiet by and large. So these are three different IOA, IOC events. So here's a lot of these arc-like structures, right-hand polarized, and then here comes the IOC event, left-hand polarized, we think coming from the southern hemisphere of Jupiter. And then you have these, we're not sure what these are called. If that's from non-IOC or is that part of some IOA. But these, again, are very repeatable structures. And you see the upper frequency limit to the IOC is much lower than the IOA. Why is that? The southern hemisphere of Jupiter, because the dipole is offset towards the northern hemisphere, the magnetic field is stronger in the northern hemisphere than in the southern hemisphere. So you don't get as high frequency from the southern hemisphere. So we can use these observations to test some of the CMI theory and ask the question, are these modes limited to each hemisphere, or maybe they're coming from the same hemisphere? So these are open questions. Kazumasa showed you this slide where we have these beautiful modulation lanes. So the LWA instrument really has excellent resolution. We can get resolutions down to 0.2 of a millisecond and frequency resolution of 5 kilohertz. So these modulation lanes going are seen in both polarizations are continuous. So the question is, does that necessarily say that the emissions are coming from the same hemisphere? I think we think so. So that then would argue against this LORX mode being opposite poles. Well, I should clarify that both modes are emitted in each hemisphere, but the O mode is much lower in magnitude. And so these new observations are essentially, testing the theory. So you've seen these beautiful IOB structures from Voyager. Now here's one from the LWA. These are the Faraday lanes, beautiful Faraday lanes seen with the LWA data. Modulation lanes, when you measure the slopes, they match up pretty well with prior data. So this is the Rahima, old Rahima data here. Plenty of S-burst. So we have the resolution that's we're able to look at some S-bursts here. So this is drift rates that we've measured, and again, these drift rates that are measured are consistent with prior measurements. But something that's kind of interesting, this is an IOB event. This, we believe, is an IOD source, Southern Hemisphere source. As far as I know, I've not seen in the literature any S-burst measured in the IOD region. So that may be something new. Again, very repeatable kind of structure. This is the IOC event. There's the lower end of the bandwidth there, showing almost down to 11 megahertz. It's a very clean spectrum. It's really a great site for doing Jupiter studies. I should mention that this antenna is fairly new, and so we actually made some Jupiter observations as a way to help them test their antenna and to check their polarizations. And what source do you think we used to check to make sure we were getting we had the right hand and left hand polarization correct? IOB. I kid you not. We actually used the IOB emissions to triple check that they had their antenna wired up right. It's really kind of cool and very easy to mix up, as Dick had mentioned. So here's some of the S-burst when you kind of zoom in on some of these regions. So really a nice data. Here's a graph of the slopes, the drift rates, I'm sorry, of the S-burst as a function of the frequency. And so the current theory says that there is a peak around 30 megahertz or so where the drift rate should change. So here's a few of the observations that we've made so far, and we're hoping it will get some data up in this region to see if this really does turn over like the theory suggests. These are data from other observatories, but the LWA should be able to make some great observations to test this model. And you've already seen plenty of S-bursts. So here's a few S-burst and N interactions here. So these are coming, as Jim Brown showed you, that before the IOB, the main IOB source, you see a lot of S-burst structure. That's fairly routine. That happens all the time. And again, why is that? Why do we see the S-burst at the onset of the IOB events? We're not sure. The configuration of the magnetic field and the cones and everything must be right to get these types of emissions. But it's very repeatable. And so great resolution here. You can really see the S bursts and these sort of little mini N bursts interacting with each other. So it's incredible that, you know, Dave and others are getting the same sort of resolution now on these structures in Jupiter's emission with, I guess I'll say, a multi-$1,000 telescope compared to a multi-million-dollar telescope. But again, we don't need this telescope for Jupiter, as others have shown, but we can do great things with it. So a couple more graphs. So this is the really nice IOB. Here's some left-hand emission we think is IOD, Southern Hemisphere. And Jim Brown, I don't know if those are N bursts. I think you hit it right on the head. And I think whatever oracle you consulted last night, or whatever you drank or smoked or something, you got it right. These new instruments, the technology has improved, the resolution has improved. We're seeing structures that we haven't seen before. We don't know what to call these things. This is awesome. This is fun. This is we are right on the tip of, the forefront of science. And, I don't know, maybe when you guys walk out of here, you're no longer amateurs, so you may have to change the name of Sarah. But anyway, it's been a lot of fun, and so I've got a boatload of data that I'm going to be analyzing this fall. I'll be on sabbatical working with Jim Tiemann and others up at NASA Goddard. And so this is our first paper with the LWA data, and so we're pretty excited to have that out, and hopefully some more to come. But I hope I'll come back and update you on what we're doing with the LWA in the future. So thank you very much. Question?
Yeah, just a comment. I think what really also makes a difference is the cleanliness of the interferences. Almost no interferences.
Yeah, it's a very interference-free site, as it is sort of around here for different frequencies. But yeah, it's a great.
The low power instrument in Europe, it's probably much more sensitive because there are much more antennas, but they are in the middle of Europe.
Yeah, right.
There's no quiet zone there.
Yeah. So hopefully this site will stay quiet. But with all the money they're pumping into the antenna out there, and it's near the VLA as well, so hopefully that'll stay a quiet site.
Oh, do you know they have an LWA in Owens Valley too?
Yeah. This is the Owens Valley. So some of you visited there, right?
Yeah.
You had a regional meeting there, Sarah did. So Owens Valley, California, they now have a sort of another arm, another pod of these LWA antennas there. And I just heard last week that they got funding for a third site for 256 LWA dipoles. So one of the guys that works at Owens Valley, oh shoot, I can't think of his name, but an Irish guy, super nice guy. He told me, I was at a science meeting I ran into him, and he told me, he goes, the first receiver I ever built was a radio Jove receiver. And this guy is now working at LWA as one of the main science people there. I thought that was really cool.
The antenna is cross dipoles in an inverted V configuration, which normally gives you some horizontal, some vertical polarization. And I assume it can be switched right hand, left hand, or any combination.
Yes.
Of
but it's measuring both
north,
simultaneously.
south, east, west, and so on. What was the reason for setting it up in an inverted V configuration, giving you that vertical component?
I think I don't know the answer to that question, but do you know?
Yeah. Actually, those inverted V thick dipoles, they have a very wide antenna ability.
Yes.
So they are almost seeing the full half sphere at once if you just combine the two. And then those are static dipoles. And so they have to observe the full sky
Yes.
each time. And then it's a software, it's in the software once you
Yes.
have the waveform that you do the correlations. And so you have to have equal gain in all directions in order to be able to do the correlation afterwards in a beam direction.
Yeah, it's incredible. It's all done by the software that's taking each individual antenna and combining them together to get the polarization out of it. So post detection essentially. Now, the other thing about this instrument, when it's fully, I guess their aim is to get arc second resolution on the sky at these lower frequencies, which has never been done before. So think about that. So your typical antenna beams are many degrees wide in some cases. Now you keep adding antennas and bringing that beam narrower and narrower and narrower and narrower, and now you're sub-degree, sub-arc minute. Now you're getting down to arc second resolution for doing extragalactic work. So that's the goal, and this is a part of this low frequency part of the spectrum. This thing is set up for I think 10 to 88 megahertz is their part of the spectrum, which has never really been studied at that resolution for galactic and extragalactic work. So that's really the driver. And then the LOFAR instrument in Europe, the square kilometer array that someone mentioned the other day. So this is, again, the advancement of technology has allowed to get to this point. And the antenna design also is fairly inexpensive. Each individual antenna is not terribly expensive. So it's really maybe a little renaissance here in radio astronomy due to the electronics that we're having right now, which is really fun.
Just a simple question here. The antennas in the picture look almost like they were kind of randomly organized. I was wondering, is there a geometric pattern or is it truly random?
I think it is random.
Yes, it's random.
And again, so you get, I guess, equal coverage of the sky with and I know they have a couple of outrigger sort of antennas that they do some testing with as well. But
A large number of baselines, right?
yeah.
And actually, you have a large number of baselines, and it's when you do a Fourier transform that the space plane, not time domain, so it's a bit complex. But the idea is that when you rebuild the antenna, the image after it gets the signal, you have much less artifacts if you use a random configuration than if you use a
okay. I see.
Not it's a regular interferometer, and you will have fringes and things like that you don't get, because here all the fringes are smoothed out because of the randomness.
Right, okay, I didn't think about that. All right, good. Mm-hmm.
Just wandering down through the field here, I see one or two similar antennas. I'm sure it's not part of the array, but is there anything being done here? Just a sense?
Array.
Yeah, I know that they did some testing here, but I don't know that they're using them now or not. Does anyone know?
You take them all?
Yeah, so the University of Virginia has, Charlottesville has, that's where the NRA headquarters are, so I think there's some scientists doing some testing on them, so I don't know.
There's a real good website about it, and there's like an 88 or 90 page about the antenna and some of the sites.
Yeah, and the LWA site has a lot of good information there that's freely available. The engineering stuff is up there.
And one of the guys that had something to do with the antennas local.
Here,
Well, I mean, he's at, I think
Charlottesville. Yeah.
You're down by the GBT, there's just one right there by the side of the road.
Yeah, I haven't made it down.
Won't be that long.
Oh, okay.
Yeah, one of the prototypes was Steve Ellingson's antennas down at Virginia Tech.
Yes, Steve is one of the main.
There were some earlier versions of that 10 years ago.
Did you? Yeah.
I was going to ask, how complicated are they? Would they be useful for, if you had a few of them, would they be useful for Radio Jove for an individual? or a smaller
Yeah, we're already having these discussions amongst the Radio Jove team, is how can we get our hands on them? They're ballpark, I think, about $1,000 an antenna. And one of the, Whit Reed in Anchorage is actually got some of these things, and I think he's selling them. So you can actually buy these things, and others are looking in China for some, for maybe a cheaper version of these things. But yeah, I think we're gonna eventually get our hands on a few of them, and you probably need 4 or 8 of them together to be good enough to do some stuff with Jupiter.
You know, some PVC and some wire, maybe.
Right.
Yeah, well, the drawings are out there. You can build your own, but could you do it cheaper than just buying the thing? I don't know.
Actually, we did some testing in Lancet with the same antenna, and with the 16 antenna in the mini array configuration, 16, we get the same sensitivity than the Decametric array with the TPs, which are 144.
Wow.
So, yeah.
That's amazing. Yeah.
Is the size of their distribution important? In other words, how far apart they are from one another?
Yeah. Actually, this is the funny thing. That antenna, we are building a new radio telescope in Lancet also, and we did an independent study of what antenna we would need, what design.
Yeah.
And we immediately arrived to a design which was very similar to that one. And so we just decided to take it because
Yeah. They've already figured it
already
out.
there, and
Yeah.
that's exactly what we need. So it's really a good solution.
Again, I think this is all driven by technology. Software is now has the ability to do, the computing power is there to do this kind of stuff. So, as I said, I think this is a bit of a renaissance we're having here, which is good for us. Any others? Okay, thanks so much. We'll break for lunch and be back here at 1:30.